Stored in the vaults of the world's major banks are thousands of tons of gold, the world's currency reserves. Gold is traded, used as a means of payment and worn as jewellery, but for chemists it's just an element. One element less precious than gold is iron. In a molten state, it can be worked with ease. Ever since the Industrial Revolution, iron has been the world's #1 material. Neon light fills rooms and brings colour to the night. Neon, another element, is one of the noble gases used in fluorescent tubes. A form of carbon, diamond, is the hardest and, at the same time, probably the most coveted substance known to man. Diamond differs from ordinary coal solely in the configuration of its atoms. A small but significant difference. Diamonds are associated with power and wealth. For centuries, man strove to unlock the secrets of the elements, but the methods he applied were just as confused as his concepts of the structure of matter. It wasn't until the early 19th century, when atoms were identified as the basic building blocks of nature, that a foundation was laid for understanding what all the various elements have in common. An element is a substance that consists of only one kind of atom. The atoms of the various elements differ from one another in that they have their different weights. Chemists used a balance to determine the ratio between the weights of the various atoms, but they came up with conflicting results. So in 1860, a congress was convened in Karlsruhe, Germany, to put an end to the unseemly situation with regard to the definition of atomic and molecular weights. It paved the way for a more comprehensive systematization of the elements. Two of those at the Congress, Dmitri Mendeljev from Russia and Lothar Meyer from Germany, both realized that the atomic weight was the key to classifying the elements. In 1867, Mendeljev was appointed Professor of Chemistry at the University of St. Petersburg. On his excursions to nearby quarries, he looked for minerals so that he could show his students in what form the chemical elements occur in nature. As a university teacher, Mendeljev published his classic textbook, The Principles of Chemistry. In the course of writing it, he probed deeply into the relationship between the properties of elements in an attempt to devise a system of classifying them. St. Petersburg, 1869. Members of the Russian Chemical Society listened to a paper in which Mendeljev summarized his findings. He had succeeded in classifying the chemical elements in a meaningful system. But how did he arrive at this system? When you are searching for something, he said, whether it be mushrooms or some kind of dependence, all you can do is observe and experiment. So, after I had written down the elements with their atomic weights and basic properties on various cards, I began to collate elements that were similar and had atomic weights that lay close together. As a result, I quickly deduced that a periodic dependence exists between the properties of the elements and their atomic weight. Mendeljev closed the gaps in his table with cards for elements that hadn't yet been discovered. He even predicted their chemical properties. Many colleagues thought his conclusions too far-fetched. The periodic table of the elements as we know it today. It consists of rows and columns. In the rows, the elements are arranged in order of increasing atomic number. This is roughly proportional to their atomic weight. The columns contain elements with similar properties. Mendeljev was unable to classify some elements correctly. Lothar Meyer devised a similar system to the Russian, but he was able to classify the elements more accurately. His chart of the periodic or recurring properties of the elements is particularly impressive. But Meyer warned against filling the gaps with undiscovered elements. In doing so, he failed to recognise a particular strength of the periodic system. In 1886, Clemens Winkler closed one of the gaps that Mendeljev had left open. He discovered the element germanium. Its chemical properties confirmed what Mendeljev had predicted. Germanium belongs to the same family of elements as carbon, silicon, tin and lead. The accuracy of the periodic system was underlined by the discoveries made by William Ramsay. Between 1894 and 1898, he identified a series of noble gases, a new and separate family of elements. Ramsay discovered the noble gases in the atmosphere where, because of their chemically inert behaviour, they had been able to remain undetected for so long. The noble gases fitted into the periodic system without any problem. But only after it was discovered that atoms consist of nuclei and electrons could the periodic system be really understood. Electrons are arranged in shells according to specific laws. When one shell is full, a new one is created. Since the chemical properties depend in particular on the number of electrons in the outer shell, with each new shell, these properties are repeated. At the same time, a new row begins in the periodic table. The hydrogen atom is the lightest atom of all. The atoms of nitrogen and of oxygen, the two main elements of our atmosphere, are many times heavier. That's why the first airships, for example, were filled with hydrogen gas. Hydrogen has an atomic weight of roughly 1. The atoms of the heaviest of all the elements that occur naturally, uranium, are well over 200 times heavier than those of hydrogen. Apart from promethium, by 1940 all 92 elements, from hydrogen through to uranium, had been discovered. In the late 30s, various groups of scientists tried to create heavier elements from uranium by artificial means. In 1938, German chemist Otto Hahn discovered nuclear fission, more or less by chance. Together with his assistant Fritz Strassmann, he was studying uranium samples he'd bombarded with neutrons. But instead of a new heavy element, Hahn only obtained lighter elements formed by the disintegration of the uranium atom. Otto Hahn had thus provided the first proof of nuclear fission. 2 years later, in carrying out similar tests, American scientists created the first artificial element, neptunium. This was followed a year later by plutonium. Neptunium and plutonium, which are heavier than uranium, were also incorporated into the existing periodic table without any problem. And all the indications were that there had to be other transuranic elements, as they are called. When it became known that the plutonium isotope 239 is easily fissile, the military took an interest. They were interested in the formidable explosive force that could be generated. Plutonium is formed when naturally occurring uranium is bombarded by neutrons in nuclear reactors. The critical mass of plutonium needed to make an atomic bomb is 5 kilograms. Up to that point, it had only been possible to manufacture plutonium in such minute quantities that they could only be weighed with the help of a fine glass thread. But even so, scientists were still able to determine the physical and chemical properties of the element. This was an important prerequisite for manufacturing plutonium by the kilogram. Using plutonium to make an atomic bomb was one of the 4 goals of the Manhattan Project. The other 3 focused on uranium as an explosive. The aim of the project was to provide a superweapon in the war against Hitler's Germany. It was the biggest scientific and military enterprise the world had ever seen. 180,000 people worked on building the bomb. Scientists and engineers were breaking new ground. What had seemed impossible became reality. But the bomb was never dropped on Germany. By the time it was ready, Germany had been defeated, but the war in the Pacific was still raging.
3, 2, 1.
On August the 6th, 1945, Little Boy exploded over the Japanese city of Hiroshima, the first atomic bomb ever dropped on an enemy. Little Boy contained 60 kilograms of uranium and had an explosive force equivalent to 14,000 tons of TNT. 3 days later, a second bomb devastated Nagasaki. Containing 8 kilograms of artificially produced plutonium, it had an explosive force equivalent to 22,000 tons of TNT. On November the 2nd, 1952, a plutonium bomb also provided the necessary heat for nuclear fusion. It was on that day that the United States exploded the world's first hydrogen bomb at Eniwetok Atoll in the Pacific. Remote-controlled aircraft flew through the dust cloud to collect samples. They were found to contain 2 new elements, which were named Einsteinium and fermium. Large quantities of these elements were found in the coral on neighbouring atolls. The 2 superpowers, the United States and the Soviet Union, embarked on a race to discover more elements that could be produced artificially. The example of plutonium had shown that they could mean military superiority. In this way, the Cold War contributed to the periodic table being extended through the addition of new elements. Since the early 80s, reports of new artificially created elements have come from Germany. Up to 1996, half a dozen new elements had been produced at the Institute for Heavy Ion Research in Darmstadt. The experiments are complex and costly. Samples have to be bombarded with atoms for weeks on end. And, to the outsider, the yield of new elements is often disappointingly low. So it's all the more fascinating to know that individual atoms of these elements can be identified. In the beginning, it was chemists who supplemented the periodic table with new elements. Today, that task is accomplished by physicists. The periodic table of the elements, the system devised by Lothar Meyer and Dmitri Mendeljev well over a century ago, has proved so universally valid that each new discovery by nuclear physics has merely served to confirm it.